Yes. Yes. I could just have you on just my go with your
Yeah, sure.
computer. I think it came with plug in the back.
Ah, okay, great. Testing, testing. You guys hear this?
Yeah, I can hear you.
Hooray! Okay, great. Thank you very much.
Glad to see you.
Yes, me too. Okay. So I have 9 a.m. We should probably give people another minute or two. Sure. It's pretty crowded. I know. Where's everyone gonna sit? 42. Okay, everybody online hears me okay? Camera's focused all right? Font is big enough?
Yeah, it looks good to me.
Great, thank you. Okay, I have 3 minutes past, so we should probably go ahead and dive on in. Najee, I think I have the answer to your question, so if you want to stick around afterwards, I'm happy to discuss. Najee had an interesting question at the end of last class about why it is that orbital angular momentum has to be integer values, but spin angular momentum is the one that can be half integer values. Why can't you have half integer values of orbital angular? Okay, so probably let's go ahead and dive on in. So let's remind ourselves what we worked on last time. We discussed spin as the angular momentum associated with internal degrees of freedom. That if you have a wave function that's not just a scalar assigning a value to every point in space, then in addition to rotating the spatial argument, which is performed by the orbital angular momentum, you have to rotate the internal degrees of freedom as well. And that extra angular momentum that's necessary to rotate the internal degrees of freedom is called spin. So when you have both orbital and internal degrees of freedom, the total angular momentum that governs rotations is not just orbital angular momentum, a derivative with respect to angle or r cross p, but the sum of orbital and spin components. And we talked about the peculiar feature of half integer spin, that it is allowed to change sign of the wave function under 2 pi rotations. So that if I take the unitary operator that rotates by 2 pi about any angle, about any axis n, the wave function changes sign. This is a uniquely quantum mechanical feature that I can take the universe, rotate it by 360 degrees, and things can change sign. And that's possible because quantum mechanics works at the amplitude level or the wave function level, but the wave function is not an observable. All observables are invariant if all wave functions change sign. And one of the ingredients that we're going to need to use today is that we took the case of spin 1/2, and we were able to explicitly construct the finite angle rotation operator because it's possible to exponentiate Pauli matrices in closed form. So when we wrote this as e to the minus I over h bar s dot theta, and wrote s as h bar over 2 times the Pauli matrices, that lets us split it up and write it sort of like Euler's formula into a cosine theta term, a sine theta term, the even powers of n dot theta squared to give us 1. And so all of the cosine terms come with the identity matrix. All of the odd powers square back, and then they just give you 1 linear power. So all of the odd powers that gave us sine in the Taylor series come with n dot theta. Okay. So before we dive into the more technical bits, maybe let's spend a few minutes getting the notation very clear, because there are lots of different representations of what the spinor information looks like, especially for spin 1/2. We said the natural basis to describe the spin states are just like for the other angular momenta in 3 dimensions. They are the simultaneous eigenstates of s squared. These eigenvalues are h bar squared s, s plus 1. And they are the eigenstates also of one of the projections, usually taken to be sz. For the moment, I'm calling this second eigenvalue sz. It's often referred to as m sub s. or the magnetic quantum number associated with spin. So one thing to point out is that the total spin angular momentum, so this quantum number, is specific to the particle itself. This is never going to change. As soon as I tell you I'm talking about an electron, I'm telling you S equals 1/2 today, tomorrow, and forever. So often it's redundant to just repeat that information. So sometimes you will see the kets notated without labeling the magnitude of the quantum number. And that's just implicit because you already know what kind of particle you're talking about. So first comment. So you'll just remember that S equals 1/2 for an electron, for example. So that's first comment. Second comment is that the spin states are often represented as a column matrix without further clarification as to what that refers to. So if I have a general spin state, let me call it chi, for a spin 1 particle, for example, then I can write this as some linear combination of that basis. So when I write these down, I'm going to ignore S equals 1. That's just implicit. I'm talking about here the case S equals 1 for all of these states. And so I just have the case SZ equals plus H bar or plus 1. SZ equals 0 plus gamma, SZ equals minus 1. This is often just written without further explanation as the column vector alpha, beta, gamma. And so it's up to you to remember what kind of particle you're talking about, S equals 1, and that each of these entries corresponds to each of these different states. So usually the one at the top is the highest spin value. And so similarly, just squeeze it in here in the corner, for spin equals 1/2, you'll often represent the spin state as just a 2-component column vector alpha beta, where that alpha is the spin up state, meaning this is the amplitude for SZ equals plus 1/2, and this one is the amplitude for SZ equals minus 1/2. So for example, for a spin 1/2 particle, the wave function can be written psi of r really tells you not just the position information, but also each of the spin degrees of freedom. So this is sometimes written as a column matrix, something like psi plus of r, psi minus of r. And again, you need to remember what each of these things means in terms of the spin information as it's represented. So in terms of the vector space for your wave function, the Hilbert space, you need a basis that tells you both what the position information is and a basis for what the spin information is. So the combined basis for both of those things would be something like the ket R for position and the spin eigenstates SZ for the spin information. Combined basis for the Hilbert space, aka the vector space, So this is a basis that specifies the position as well as the spin information. Formally speaking, this is a tensor product, because there are actually two different vector spaces we're talking about here. We have the infinite dimensional vector space of positions in 3 dimensions, a separate vector space that is dimension 3 for what the spin components are, or dimension 2 for spin 1/2, whatever finite dimension we have. These are two independent vector spaces, and I'm putting them together to make a bigger vector space. That's what this means. So just a comment about the sort of formal basis of this. Formally, this is a tensor product. This is the vector space of positions, real space. And then this is a separate vector space of spin. And then putting those two things together, you make the combined basis for the wave function in the larger vector space that includes both spin and orbital information. So this is important because this affects how you write the completeness relations. So a complete set of states for this vector space is the integral over all position states. The complete basis for the spin is a discrete sum over all of the allowed spin states. So to insert a complete set of states for the combined space, you have to do both at the same time. So you have 1 equals sum over all spin states, which I guess formally goes from minus s to plus s. And you also have an integral over the position states, d3r. So for example, this affects the normalization condition of a wave function that has spin. It's only normalized to unity on the overall vector space, including both the spin and the orbital information. So I have the normalization condition is that the overlap of a wave function with itself is 1. If I insert this complete set of states, that's more than just the integral. So this is sum over SC, integral d3r, psi r SC, r SC psi. So my normalization condition then becomes 1 is integral d3r, the sum over all SZ projections, psi SZ of r squared. So just to be completely clear, for example, if I have spin 1/2, and my wave function psi of r is a 2-component column vector, psi plus, psi minus, then my normalization condition is integral d3r psi plus of r squared plus psi minus of r squared equals 1. All of this is pretty obvious if you think about it for a minute, but just to be completely clear so that we're all on the same page, I wanted to emphasize this. Okay. So next I want to talk about general eigenstates of spin projections. So these are projections that single out the special component SZ, There's nothing special about SZ. You can talk about SX or SY or any projection of S onto an arbitrary unit vector, S dot n. And this is useful for thinking about the physics or thinking about the direction that the spin is pointing as the physics moves it around. So here I'm talking about spin vector dot product with some unit vector n. So since we spent so much time discussing rotations and transformations of the state vector, we can immediately build something that has spin projection along an arbitrary unit vector, starting from the state that has spin projection along the z-axis, just by rotating. So here, in case I forget to specify, I'm talking specifically about spin 1/2. So if I start off with a coordinate system, x, y, z, if my spin that I'm going to start off with is the sz state, which is written in this basis as 1, 0, that's the eigenstate of spin projected along the k hat, or unit vector along the z-axis. I want to rotate that and now give you the projection along a different axis. So what I want is spin projections along the axis n, which is somewhere out there in the plane, somewhere out there in space. So we'll describe n by its spherical coordinates theta and phi. And so I want to start with the state 1, 0 in this representation and perform the unitary rotation on it that will tilt it out into the three-dimensional space and point it along n. To do that, I'm going to rotate it in this plane. And that means I'm going to use an axis of rotation that is perpendicular to that plane. I don't know how well my different colors will show up, but let me try. So I want to rotate these vectors about an axis which is orthogonal to that plane. So I want a unit vector which is proportional to k cross n. Can you guys see this red, or is that terrible? Online folks.
It's
Terrible.
pretty brutal.
It's terrible, okay. Yellow is probably no different than orange for you guys. K cross n.
That's a lot better, but white's like perfect.
Okay, I'm not sure what to do for a figure then when I've got lots of different things going on. Hopefully this is clear enough. All right, so what I want to do is I want to start with the state, start with the state 1, 0. And I want to hit it with the rotation matrix U 2 by 2 by an angle theta, that polar angle theta, which tells me how far away from the z-axis I went. And the direction of this is a unit vector U. That unit vector U is in the direction of k cross n, but I need to make it a unit vector. So U is equal to k cross n divided by the magnitude of k cross n. So if I just start with this definition of n and I start taking cross products with it, let's see, k cross I is positive j. So I'm going to get sine theta cosine phi j. K cross j is negative I. And then obviously k cross k is 0, so this third term doesn't give me anything. I have to normalize this thing to unity, so I divide by the magnitude of this vector. Sine squared theta cosine squared phi plus sine squared theta sine squared phi. The magnitude is obviously sine theta. So the vector that I need to do the rotation amount is cosine phi j hat minus sine phi I hat. Okay, so now let's explicitly construct what that rotation matrix is. U 2 by 2 of theta along the unit vector u is, let's see, cosine theta over 2 times the identity matrix minus I sine theta over 2 times the unit vector u dot product with the Pauli matrices. So here I only have an x component and a y component. So when I take this dot product, I'm going to have ux, which is minus sine phi, times the Pauli matrix sigma x. So recall sigma x is 0, 1, 1, 0. And this is going to get multiplied by minus sine phi in this dot product. Recall also that sigma y is 0 minus I 0. And this is going to get multiplied by cosine phi. So I just want to explicitly construct this matrix. All right, let's see. On the main diagonal, I have the identity matrix times cosine theta over 2. On the off diagonal, that's these guys. I have minus I sine theta over 2. And then I'm going to have, let's see, minus I and minus 1 is plus I. So, I don't know, maybe I'll fill these in off to the side for the sake of space. So I'm going to have plus I sine theta over 2 sine phi. And then in this bottom corner, I'm still writing this term, by the way. So this is just the contribution from sigma x. In here, I'm going to have minus I, and then the same thing. Minus I minus sine phi. So I'm going to get plus I sine theta over 2 sine phi. And from this second term here in the top right corner, I'm going to have minus I and minus I. That's minus 1. So minus sine theta over 2 cosine phi. And in the bottom left corner from this contribution, I have minus I and plus I, which is plus 1. So I have plus sine theta over 2 cosine phi. Okay, and so I can combine these pieces nicely into cosine theta over 2 minus sine theta over 2 e to the I phi. Sine theta over 2 e to the minus I phi. Cosine theta over 2. Let's see. So I had minus sine theta over 2. Should have had minus I and minus I to give me minus 1. Yes, cosine plus I sine. Looks right. Yes. Okay, so double check me, make sure I didn't fumble a sign here or something. This is the correct answer. All right, so the point of this is to use that rotation matrix to construct eigenstates of the spin projection operator along any axis you want. So then if I define the state plus n, as the state that I get by rotating the state that was originally aligned along the plus z axis. This is that matrix acting on 1, 0. So I just multiply 1, 0, and I get cosine theta over 2, sine theta over 2, e to the minus I5. And likewise, if I rotate the spin down state the same way, then I get minus sine theta over 2 e to the I phi cosine theta over 2. So these are perfectly good eigenstates of the operator S dot n. Often it is conventional to multiply by an overall phase to write the phi dependence in a more symmetric way. Remember that the eigenstates or the eigenvectors are arbitrary up to an overall phase. So often it is conventional to write these as plus n is cosine theta over 2 e to the plus I phi over 2 sine theta over 2 e to the minus I phi over 2. And minus n as minus sine theta over 2 e to the I phi over 2 cosine theta over 2 e to the minus I phi over 2. Either one works fine. You're not going to get yourself into any trouble if you work with these states as opposed to these states, but the textbook lists these. So now just a comment of something that you will see on the homework when I put it up on Friday. You can arrive at the same answer if you write down the operator S dot n in matrix form, in terms of the Pauli matrices and those theta phi angles coming in from n, and explicitly find its eigenvectors. That is another way to arrive at this answer. All right, so at this point, it's worth emphasizing something which is very unusual about spin 1/2. And that is that every spinner, everything that I can write in a two-component spinner with some unknown complex coefficients alpha and beta, every spinner is an eigenstate of some spin projection operator. This is generally not true for higher dimensional spin states. It's generally not true for orbital angular momentum. But this leads to some weird, like semi-contradictory information. You say the spin vector S is not an observable. S is not an observable because the different components don't commute with each other. Sx with xy is not 0. Sx with sz is not 0. Sy with sz is also not 0. The components don't commute, they do not have shared eigenstates. But you can always identify for a spinner what direction the spin vector is pointing because of this funny fact. So the loophole to this, for spin 1/2 only, which is that even though you can't specify S, you can specify the operator S dot n of which it is an eigenstate. So in this backwards way, you can figure out what direction the spin vector is pointing, even though it's not observable in quantum mechanics. Only for spin 1/2. So I will also add a small exercise about this to the homework as well for Friday. It's a simple matter of sort of counting degrees of freedom. If you have a general spinner, alpha and beta are allowed to be complex numbers. So you have 4 degrees of freedom, real part of alpha, imaginary part of alpha, real part of beta, imaginary part of beta. You have 4 degrees of freedom that go into the spinner. And in addition to that, you have constraints. You have a normalization constraint, which tells you alpha squared plus beta squared is 1 to normalize the spin degrees of freedom. And you also have that the eigenvector is arbitrary up to an overall phase. So starting with 4 degrees of freedom, the normalization condition removes one of them. The arbitrariness of the overall phase removes a second one of them, and you're left with 2 degrees of freedom that remain. Those 2 degrees of freedom are translated into theta and phi that tell you the unit vector n of which it is an eigenstate. So this was very confusing to me when I was taking quantum mechanics for the first time. I remember sitting in on a seminar and the guy had done some complicated calculation and he showed a picture of the spin vectors in his solid state calculation about what all the spins in the material were doing. And I scratched my head and said, didn't we just learn in quantum mechanics that the components of spin don't commute? So how are you allowed to show me the direction the spin vector is pointing? And the answer is this is the loophole, but it only works for spin 1. All right, how am I doing on time? 40 minutes. Okay, any questions on this general discussion of spin before we start talking about precession in a magnetic field? Okay. So, regarding precession in a magnetic field. So we already saw when we discussed the Stern-Gerlach effect that a magnetic moment, which is associated with angular momentum of a charged particle, experiences an alignment energy in the presence of a magnetic field. So if I have a magnetic field B, and you have a magnetic moment, mu, this could be due to a loop of current, classically. It can be due to a charged particle moving in some circular orbit. A magnetic moment interacts with that magnetic field according to Maxwell's laws. And this generates an energy that tries to align the magnetic moment in the direction of the magnetic field. So the energy is lowest when mu is in the same direction as B. You pay an energy penalty, higher energy, if you want to bend mu away from it. So similarly for this interaction energy, so this is the alignment energy, the force, so to speak, the generalized force associated with that alignment energy is a torque. This energy you try to minimize the energy, and that minimizing the energy exerts a torque on the magnetic moment that pulls it in the direction of mu. Pulls it in the direction of the magnetic field. So you experience torque in the magnetic field tau equals mu cross B. So the precession comes in from the combination of this statement and one other one, right? So recall that torque is defined as the rate of change of angular momentum with time, the L dt. And this is mu cross B in the presence of a magnetic field. If the magnetic moment is itself related to the angular momentum, where the magnetic moment mu is proportional with some coefficient gamma times the angular momentum, this leads to torque-induced precession. The L dt is gamma L cross B. So this coefficient gamma is called the gyromagnetic ratio. We will calculate it for a charged particle moving in a circular orbit momentarily. To see that this is precession, I think it's useful to write this slightly differently. So this is the L dt equals minus, if I reverse the direction of the cross product, this is minus gamma B cross L. So compare this to the formula for a rotation. A rotating body has V is omega cross R. So omega tells you the axis of rotation. So this is describing rotation of L, rotation of, in this case, the analogy is the position vector. It's being rotated about the axis minus gamma B. Right, so the frequency of rotation is minus gamma B. So the picture sort of looks like this. If you have the magnetic field pointing in some direction like this, the magnetic moment mu, which is gamma L, is pointing off at some angle. The torque is, let's see, minus B cross L. So I take this, B cross L would be into the page, minus B cross L comes out of the page. So this, so if it's pointing over here to the right, it's going to start moving out and in a circle like this. And so that axis of rotation here, omega, is minus gamma B. That's rotating this way. So another way to say this again, the rate of change of L is perpendicular to L. So the magnitude of L is always constant, but it's turning its direction. And it's rotating in a circle around the direction of the magnetic field. So this kind of equation is much more general than just magnetic fields. So this is torque-induced precession in general. The torque leads to a rate of change of angular momentum. You can get this with gravity and bicycle wheels. Okay, quick comment about the gyromagnetic ratio. If you have in electrostatics, or magnetostatics, I guess, you have a steady state current flowing in a current loop. The magnetic moment mu is equal to the current I going through the loop times the area of the loop divided by the speed of light times a unit vector perpendicular to the loop. So if I have a current loop here, current I flowing through it, A is the area, N is the unit vector. Actually, I guess I need to draw my current going the other way. This is the right-handed rule unit normal vector. Then the magnetic moment is proportional to the current times the area. So the analogy is now if I have a charged particle Q moving at some speed v in a circle of radius r, that generates a current. Right, so the current is the charge per unit time. That's per unit time is velocity divided by the circumference, 2 pi r. So that's like saying I see charge Q pass by this point every t seconds, where t is the period. And that period is velocity divided by circumference, velocity over distance. Times the area of the loop, which is pi r squared. And I also have a factor of c. All right, let's see. Pi cancels pi. If I multiply and divide by m, then mvr, so you cancel one factor of r. mvr is the angular momentum. mv is the linear momentum, r is the lever arm. So when I collect all these factors, I get q over 2mc times mvr unit vector. So this is q over 2mc. So this quantity, q over 2mc, is the gyromagnetic ratio for a charged particle moving in a circular orbit. This is the classical picture, but we will see exactly the same thing given back to us quantum mechanically. Yes.
I don't know if I'm just misremembering. Is the magnetic moment not just IA? Is this in like Gaussian units?
This is probably Gaussian units, yes. The rest of the textbook was in Gaussian units, so I assume the factor of C here is from using CGS units.
I remember looking at magnetic moment the last few weeks for the fall.
Yeah, good call.
Like, there's no C.
Good call. CGS units. All right, so for the quantum case, let's start by talking about orbital angular momentum, and then we'll get to spin right after that. So let's write down the magnetic field. The coupling of a particle to a magnetic field goes through the minimal coupling Hamiltonian. So recall that we had H, E, and M is P minus Q over CA squared over 2M. Momentum is an operator. If I'm taking the external magnetic field to just be a fixed external magnetic field, then this A is really just a parameter. It's not really an operator on the quantum state. Once we quantize the electromagnetic field and we start radiating photons, that will be a different case. But for now, this is just a fixed external magnetic field. So when I open this guy up, I get the free particle Hamiltonian P squared over 2M minus Q over 2MC P dot A plus A dot P plus Q squared A squared over 2MC squared. Precession is a weak magnetic field effect. So we are going to approximate, assuming that the magnetic field is weak enough that I can neglect this last term. Neglect if magnetic field is weak. This first term was just the free particle. So the part that I'm really interested in is this cross term in the middle. This is my H interaction between the particle itself and the vector potential that it's experiencing. So now I need to specify what is my vector potential. If I take my magnetic field to have a constant magnitude in the z direction, I can pick a whole family of vector potentials that will give me this magnetic field. I'm going to pick the specific one. This specific choice is divergenceless. This is sometimes referred to as the Coulomb gauge. So recall that the choice of vector potential for a magnetic field is highly non-unique. You have an entire symmetry group that you can choose between that allows you to add any complete gradient of a vector field, a gradient of a scalar field to it without changing the curl. Using that gauge freedom allows you to make a whole family of choices about what shape this vector potential has. And requiring that the vector potential have zero divergence is one of those valid choices. So I'm always allowed to specify a gauge in which the divergence of A is zero. Why does that matter? Because I'm going to show momentarily that that means that these two terms commute with each other. So writing P dot A plus A dot P as 2A dot P plus or minus the commutator plus the commutator of PI with AI. So this term is the divergence of the vector potential. So if I write in a coordinate basis, Pi is minus I h bar d dxi. Then this expression is minus I h bar sum over I d dxi ai, and this is sum over I minus I h bar sum over I dai dxi. And this is zero in this particular choice of gauge. Is this clear, or should I do this step more slowly? So this is product rule of the derivatives. Remember that this is a differential operator acting on some other function over here. So the first term is derivative of a times function, and you have to use product rule on that. The second term that I subtract is a times derivative of function. When I take the difference, the only thing that's left is the part where the derivative acts on a, and that is the divergence. Okay, so using this, I have my interaction Hamiltonian is, we had minus Q over 2MC, and then using this relationship, I replace P dot A with A dot P, because the commutator is 0, to A dot P. So this is minus Q over MC, A dot P, and now I plug in what A is. A had magnitude B over 2, And it was that circular form. It was minus y x hat, px, plus x py. This combination is precisely the angular momentum LZ. So this is minus QB over 2MC LZ, and B is purely in the Z direction. So I will identify this as L dot B. Angular momentum, and then defining that combination of coefficient times angular momentum as the magnetic moment. This brings it into the form minus mu dot B, as we had classically, and the gyromagnetic ratio gamma is exactly the same as what we had for a charged particle moving in a circular orbit. So this is with mu equals gamma L, and gamma is Q over 2MC. So that gyromagnetic ratio just fell out automatically out of the minimal coupling of the momentum and the energy of the Hamiltonian to the electromagnetic field. I do not have time. 20 minutes. All right, is this picture clear? This went by pretty fast, but all I really did was I wrote down the Hamiltonian for the electromagnetic field, a particle in an electromagnetic field, like we've done many times. I picked out the cross terms. I picked a gauge in which A is divergenceless. And then I manipulated these terms and wrote it in terms of the angular moment. Nothing really too magical there. All right, once we have it in this form, we get the statement about spin precession or angular momentum precession almost for free. We know the time evolution is governed by the Hamiltonian. So my state psi of t is equal to the time evolution operator u of t acting on the state at t equals 0. The time evolution operator is minus I over h bar Hamiltonian times time, psi 0. Now there's a free particle part of the Hamiltonian, and there's the interesting part of the Hamiltonian. I'm just going to plug in the interesting part. If I just plug in that interaction part of the Hamiltonian, minus mu dot B, or gamma L dot B, this is e to the minus I over h bar minus gamma L dot B times time. And now I just rearrange this because now this looks like a rotation operator. Rotation operator looks like e to the I L dot theta. And I've got e to the I L dot stuff. So all I have to identify is what is the stuff. This is e to the minus I over h bar L dot minus gamma B T. Cycle. So the statement is, this is a rotation operator. U of theta was e to the minus I over h bar L dot theta. So all I have to identify is what is that rotation. So psi as a function of time is e to the minus I over h bar L dot theta psi naught with theta equals minus gamma B times time. Or if I take the derivative and write it as the angular velocity, this is a precession frequency minus gamma b. So this is my rotation operator u of theta equals minus gamma b t. So we get the same picture back quantum mechanically that we had classically. The angular momentum precesses in a circle where the rotation frequency omega is minus gamma b. So this was a simple exercise because we already understand what rotations look like, and because we correctly programmed in the classical to quantum correspondence about how rotations work, how time evolution works. All of the physics is consistent. Okay, any questions on this part? The discussion about spin is almost identical, except I don't have a good starting point for how to couple spin to the electromagnetic field. And that's where the work comes in. We expect spin to do something similar, but what is the analog of minimal coupling? So before we had H free was P squared over 2m, and we turned that into the interaction of a charged particle with a magnetic field by writing P minus Q over Ca squared over 2m. The magic was just that replacement. Momentum goes to momentum minus Q over Ca. And as you guys saw on the problem for the final exam, this shift is directly related to that phase symmetry of the Hamiltonian itself. So this equation doesn't have any room for spin in it. So I'm going to call this the coupling to the electromagnetic field for a scalar particle, meaning that this is for spin equals 0. So how do I bring spin into the game? Normally, this is something that you only derive when you have the Dirac equation handy. You have to go to relativity because relativity is what forces you to introduce the Dirac matrices there to get a consistent Hamiltonian picture. But you don't have to do it that way. Let me point you to a part of the textbook much later on. This derivation is based on an offhanded comment they make in the textbook on page 569 that you can derive this coupling without needing to go through the Dirac equation first. So the way we're going to do it is just by introducing a trick, using a silly identity, and then performing minimal coupling again. So the identity is the following. Because the Pelley matrices are roots of unity, P squared equals sigma dot P squared. So I can write my free particle Hamiltonian for a spinner, H free spinner, as sigma dot P squared over 2m. And now I perform the same trick. So by minimal coupling, I'm going to get coupling to the electromagnetic field of a spinner as sigma dot P minus Q over Ca squared over 2m. And I'm going to work out exactly the same term that we did a few minutes ago, that cross term between P and A that gave us that interaction with the magnetic field, but now it's going to have a sigma in it. All right, in the interest of time, I think I will save the algebra of expanding this out. And again, you get a sigma dot P squared, that's the free particle. You get the sigma dot A squared. That's again part of the scalar coupling to the electromagnetic field. The part that I want to keep is that cross term. So the relevant part here, that interaction of the spinner, is going to give me similarly minus Q over 2mc, and now the cross term looks like sigma dot P, sigma dot A, plus the other way around. Sigma dot A, sigma dot P. All right, now I want to use another identity about the Pauli matrices that's going to tell me how to relate sigma dot this thing and sigma dot that thing. In a homework assignment last semester, you guys worked out the multiplication rule of the Pauli matrices. Sigma I, sigma j is equal to delta ij times the identity matrix plus I sum over k epsilon ijk sigma k. Sigma I, sigma j, yes. So if I just take this equation and I contract those indices with two arbitrary vectors, multiply it by AI and BJ, where A and B are completely arbitrary vectors. This is equivalent to saying sigma dot A, sigma dot B, equals A dot B identity matrix plus I sigma dot A cross B. Notice that I kept the order of the vectors the same. This equation works even if these are non-commuting operators. A and then B, A and then B, A and then B. It wouldn't work if I wrote the cross product in the other order. So this is exactly the form that I have here. So if I use this expression, I get interaction Hamiltonian for a spinner is minus Q over 2mc. So this is P dot A plus I sigma dot P cross A plus A dot P plus I sigma dot A cross P. And now I'll do the same trick that I did before. If I work in a Coulomb gauge where the divergence of the vector potential is 0, then this gives me H interaction for the spinner is minus Q over 2mc. This was 2A dot P, just like we had before. This is the orbital angular momentum part of the expression. Plus a new term coming from the cross product. Plus I'm going to write this explicitly. Sum over K, sigma I, epsilon ijk, and now this is Pj AK plus Pk AJ. Operators in the other one. AJ PK. All right, now I'm just going to manipulate this cross product. If I redefine in this term, I'm going to swap J and K. When I do that in that term, this is IKJ. I'm allowed to do that. I'm just relabeling dummy indices. I guess I didn't write that. I'm summing over all three indices here. IJ and K is the triple product. When I relabel these things, I can use the anti-symmetry of the Levi-Civita symbol, minus IJK. So when I do that, that turns this into a commutator. So this piece is I sum over IJK, sigma I, epsilon IJK, and now this is the commutator PJ AK. This one minus that term. So you see this is a real commutator. And in the same way as before, if I take this object and I go to a coordinate basis, then my PJ is minus IH bar derivative with respect to XJ. And this commutator gives the term where that derivative acts only on the A field. So you can see where I'm going with this. This is going to give me curl of the vector potential. All right, so we had 2A dot P plus, let's see, I have I, and then I have minus IH bar. So I just have plus H bar, and then I have sigma dot curl of A. What is curl of A?
0.
Not 0. It's something with physics in it.
Something with B.
It is B. It is the magnetic field. Curl of the vector potential is the magnetic field B. So this is minus Q over 2MC, 2A dot P, plus H bar, sigma dot B. This was the heart of the derivation. We've already worked out what this first term is. So if I plug this back in, this was minus Q over 2MC. This first term was, let's see, L dot B. Plus, if I just multiply and divide by 2, this is H bar over 2 times 2, sigma dot B. If I pull out the magnetic field, this is L plus 2S dot B, where the spin is H bar over 2 times the Pauli matrices, S. The entire point of that derivation was to get that damn factor of 2. So what we find is that for a spinner, H E N M spinner, I guess I should say H interaction, is minus mu dot B, just like before, but the magnetic moment now receives 2 contributions. It is gamma L, just like before from the orbital stuff, plus 2 times S. This factor of 2 is sometimes called G. This is called the Landé G factor. And this is something unique about spin, that coming from the spin 1/2 case, it couples to the magnetic field twice as strongly as orbital angular momentum does. And this is a direct consequence of the algebra of those Pauli matrices. Okay, I believe I have 0 minutes remaining. Actually, I have 3. Excellent. Okay, this was the main crux that I wanted to get across. So in the textbook, in the section on angular momentum and spin in chapter 14, they basically just say, We already did this for angular momentum. Now let's just assume mu for the spin is g times gamma times s, or some g. And then by magic, you get g equals 2. The statement in the textbook is that g equals 2 is a consequence of the Dirac equation. It is a consequence of the Dirac equation, but you don't need relativity to get it. It's a consequence of the algebra of the Pauli matrices. And the Dirac equation is one way to force you to bring in the Pauli matrices. There's also a nice little discussion in chapter 14 on spin about the fact that experimentally and even theoretically, g is not exactly equal to 2. And this part is just extra for your information connection to ongoing research status in the field. G is not equal to 2 exactly. This g equal to 2 expression that we derived is true at lowest order in perturbation theory. This was true because we had an external magnetic field that was not dynamic. For a static external field, g is equal to 2 exactly. So if I draw a picture associated with this, I would say I have something like an electron, which comes in, it gets hit by the magnetic field B. And right at that interaction, this elementary coupling coming from that interaction Hamiltonian corresponds to g equals 2. The electron comes in, it gets hit by the magnetic field sees g equals 2, and the electron goes back out. If my photon, however, is dynamical, if I quantize the electromagnetic field and I start to allow the electron to emit photons in perturbation theory, then this picture changes. This is now just the lowest order possible process in perturbation theory. And you get a sizable correction coming from something that looks like this. So this looks like the wave function where your electron came in and your electron radiated a photon. And it split off like this. Electron, electron, photon. In that splitting, there's a conversion between spin angular momentum here and orbital angular momentum of the photon-electron system. So this quantum fluctuation, which is perfectly allowed, changes what that electromagnetic field sees. And when the electromagnetic field interacts not just with the bare electron, but the quantum fluctuation into a photon-electron system, this overall interaction sees g not equal to 2, because it couples not just to that bare vertex, but to the orbital angular momentum that was generated in the split. And so you can calculate in the theory that you need to do this is quantum field theory, because you need a fully interacting theory that allows you to radiate as many photons as you want. In quantum field theory, the theory is called quantum electrodynamics. QED. Then you can calculate exactly those diagrams, order by order in perturbation theory. And there are all kinds of corrections like this, and some of these are actually pretty pathological. And you have higher order corrections coming not just from one photon emission, but from 2 photon emission. And all orders in perturbation theory. Everything that can happen does happen in quantum mechanics. But this allows you to calculate g minus 2 equals, or let me say, g equals 2 times 1 plus the first order perturbation theory plus second order in perturbation theory, and so on. This calculation is one of the milestones of QED. You can calculate this correction to astronomical precision in the theory because the fine structure constant, 1 over 137, is incredibly small. So you have the ability to calculate order by order in perturbation theory to excellent approximation. The last comment that I'll leave you with is this process is highly sensitive to non-standard model physics. In addition to photons, what if you have your favorite theory of dark matter or supersymmetry or anything? And your theory says my electron can interact with things other than photons. Those things contribute here too. So if you have a new particle, those things can also start entering these loops. And so the experimental measurement of G-2 is extremely sensitive to the presence of beyond the standard model particle physics. And so this is why there is a very expensive high precision effort going on to measure the G-2 of the muon at Fermilab, where they have a gigantic accelerator that they are using as a muon storage ring. You generate a whole bunch of muons that are just like electrons but 200 times heavier. You keep them trapped in that orbiting magnetic field and you measure their spin precession. By measuring the frequency of the spin precession, you measure their magnetic moment and you measure G-2. And if you can measure tiny deviations from the predictions of quantum electrodynamics, then you can potentially be sensitive to discovering beyond the standard model of particles. All right, that's it. Thank you, guys. I will see you next week where we will pick up with addition of angular momentum, spin plus orbital angular momentum. Thanks, guys. And then